All right, let's dive into the incredible adventure of force and pressure. We're going to uncover some of the invisible rules that, well, basically run our entire world. It's a story of pushes, pulls, and some pretty amazing power. I mean, have you ever really stopped to wonder about it? What makes that soccer ball soar through the air? Or why does an apple always fall down from a tree and never up? It almost seems like magic, right? Well, it's not. It's physics, and we're about to pull back the curtain and see how it all works. So, every great adventure needs a hero. And our story begins right here with a hero who's just waiting for a call to action. Everyone, meet Mo. Right now, Mo is just a simple ball at rest. And at rest is just a fancy science way of saying he's totally still. He's not going anywhere. So the big question is, what's it going to take to get Mo's incredible journey started? See, here's the thing about Mo. He can't just decide to start moving. It's impossible. To get his adventure going, he needs something else to step in. He needs to meet the very first, most basic rule of motion. And that something is called a force. Seriously, it's that simple. In the world of physics, a force is just a push or a pull. That's it. This is the real hero of our story, because it's the one thing that can get Mo up and moving. And once you start looking, you see forces absolutely everywhere. When a goalkeeper makes a save, that's a push. When a hockey player smacks the ball to change its direction, that's a push too. Kicking, lifting, throwing, it's all just different ways of saying you're applying a force. And force has some seriously cool superpowers. It can take our hero, Mo, from a dead stop to top speed. It can stop him cold, make him go faster, or make him slow down. It can totally change his direction, or even change his shape. You know, like when you squash a rubber ball. But what happens when more than one force shows up at the same time? Well, things get a little more interesting. And suddenly, Mo finds himself right in the middle of a great cosmic tug-of-war. This is a perfect way to picture what scientists call the net force. If two forces are working together, like these two friends pushing the box the same way, their forces add up. But if they push against each other, they start to cancel each other out. The box might not move at all, or it'll move in the direction of whoever's pushing harder. The classic tug-of-war is the perfect example, right? If both teams are pulling with the exact same amount of oomph, that rope isn't going anywhere. We call that balanced forces. But the second one team pulls just a little harder, the forces become unbalanced, and that's when you see movement. The winners are the ones who applied the greater force. Simple as that. Okay, so Mo's journey is about to get even more fascinating because he's about to discover that not all forces are obvious. Some of them, well, they like to work in disguise. You can basically sort all forces into two big families. First up, you've got your contact forces. As you can probably guess, these forces have to actually touch an object to do anything. Then you've got the really mysterious ones, the non-contact forces. These guys can push or pull from a distance, almost like magic. A super common contact force is muscular force. Anytime you lift something or you see animals pulling a heavy cart like this, that power is coming from the action of muscles. Our bodies, or their bodies, have to be in direct contact with the object to get it to move. And then there's friction. You can think of friction as the kind of villain in Mo's story. It's a contact force that always, and I mean always, pushes in the opposite direction of motion. It's like a sticky shadow, always trying to slow Mo down and bring him to a stop. Okay, now for the magic. We all know magnets can pull or push each other without ever touching. Or think about this. If you rub a straw with some paper, it can actually pull another straw toward it through something called electrostatic force. These are non-contact forces, and they act like invisible hands reaching across space. And the biggest, most famous non-contact force of them all is, of course, gravity. It's not just about apples falling out of trees. Gravity is this universal force that pulls every single thing in the universe towards every other thing. It's what's keeping Mo on the ground right now, and it's what keeps planets in their orbits. It's always there, always pulling. So now we get to the real climax of Mo's journey. This is where we learn that it's not always just about how much force you use, but how you use it. Welcome to the part of the story called Under Pressure. Let me ask you a riddle. You can hit a nail with a hammer using the same amount of force on either end. So, why does only the sharp, pointy end go into the wood? The answer is the key to this whole section. The secret is pressure, and pressure is just how concentrated a force is over a certain area. Look at the formula. Pressure equals force divided by area. So what does that mean? It means if you use the same force, but you make the area way, way smaller, the pressure gets way, way bigger. This picture shows it perfectly. The hammer is delivering the same force no matter what, but all of that force is focused on the teeny tiny point of the nail. That creates immense pressure, enough to pierce right through the wood. On the flat head of the nail, that same force is all spread out, so the pressure is super low. And get this, the pressure from the air all around us is also unbelievably powerful. Way back in the 17th century, a scientist took two metal half spheres, put them together, and pumped all the air out. The air pressure from the outside was pushing in so hard that not even two teams of horses could pull them apart. That's the power of atmospheric pressure. Wow. So, after this incredible journey, Mo has learned all the rules of force and pressure. Now it's time for his final challenge, to see all of these rules working together all at once. Let's just look at an archer. First, she uses her muscular force, that's a contact force, to pull back the string and change the bow's shape. When she lets go, the bow springs back and applies a contact force to the arrow, sending it flying. And while that arrow is in the air, two more forces take over. The non-contact force of gravity is pulling it down towards the earth, and the contact force of air friction is slowing it down. See? It's all there in one single action. And that brings us to you. You've been on this whole adventure with Mo. You know the rules now. So here's the final puzzle. What forces are acting on you this very second? Just think about it. You've got the constant non-contact pull of gravity holding you down, and you've got the contact force of your chair or the floor pushing right back up at you. The incredible story of force and pressure, it's happening to you all the time.